Okay, we got one more to go, and it's a good one. Our big finale. The limit as x approaches 0, sine of x raised to the x. What are we going to do with that? Well, this might look kind of familiar. We did a variable raised to another variable before when we looked at logarithmic differentiation. We need the same approach here. We're going to have to rewrite this as a ratio, a numerator and denominator, to use L'Hopital's rule. We definitely don't have that right now. So we're going to begin by saying, let's just call this y, so that we can then take the natural log of both sides. Once we have the natural log of both sides, that allows us to move this x down in the front, giving us a product. But even that is not going to be helpful with L'Hopital's rule. You need to make it a ratio. Let's go with the natural log of sine x over x to the -1. And now we've got a ratio. Now you might say, hey, is there maybe another option besides this? Yeah, you could say, in theory, you could say x over natural log sine x to the -1 and perform derivatives this way. But I'll just tell you, this is not the way to go. Don't do it like that. We'll go here with the x in the bottom. Okay. So what we're going to do is apply our limit to this guy right here. Now, when we do that, we think, wait a second, but the sine of x raised to the x, we took a natural log at one point. Like, this is not the same as the original question. If we take this limit, that's true. But we're going to do the limit of this ratio, but then at the very end, after we get an answer, we're going to recognize, hey, this was the natural log of y. We just want the limit applied to y, and we'll be able to, reverse this natural log that we did way back at this point. So let's take the limit as x approaches 0 for the natural log of sine x over x to the -1. We never checked if it was indeterminate, did we? We did it at the very beginning of this section, but okay, if we plug in 0 raised to the 0, we're good. You could recheck it again for your ratio. It'll still be indeterminate. I think this time you'd have -infinity over infinity. You don't have to do it twice for the different form. Okay. Let's perform our rule here carefully. The natural log of sine x, that's a chain rule. 1 over sine x times derivative of sine is cosine x. And it's over this derivative, -x to the -2. That wasn't too bad. Okay. Well, let's think about this. Let's clean it up a little bit. Let's see. As I look at that numerator, cosine x over sine x, I could call that cotangent x if I really wanted to. I think, though, I'm not. Let's see. The x to the -2, I'm going to move up. I'm going to call this, you know what, just for a second, this is -x squared cotangent x. But I'm more familiar with tangent. Let me call this -x squared over tangent x, and that would be the same thing. I'd rather think of it this way, just my own comfortability with tangent versus cotangent. Maybe you feel the same. And also, check this out. If we try to plug in 0 here, what's going to happen? It's going to be 0 over 0. Tangent of 0 is 0. So we've got another indeterminate form. And guess what? We got to do L'Hopital again. As you can see, it's really common to have to do more than one L'Hopital. This time we get negative 2x over derivative tangent is secant squared x. Secant squared is the reciprocal of cosine. You know what, let's leave it like that and just kind of, we'll see what happens. Okay, what happens if we plug in 0 at this point? What is the secant of 0? Well, you can find that by taking 1 over cosine of 0. And we need to square here. Turns out cosine of 0 is 1. One over cosine squared 0 would equal 1. So this whole denominator is 1. That's just that we're looking at. So, not the limit. We plug in 0, we'd get 0 over 1. And so the answer to our limit is 0. Okay, we're not quite done yet. Remember, we got to reverse that natural log that we did earlier. We have found the limit for this guy. Really, we want to think of it as we found the limit as x approaches 0 for the natural log of y. But the original question was just y. So how do we go from knowing the answer for the limit for the natural log of y back to just y? And well, what cancels out a natural log? It's e. We want to know the answer to this. Then we take e to the power of our answer here. And e to the 0, of course, is 1. And so there's the answer to the original function. You're kind of wondering like, wow, what is that all about? You know, I don't quite follow that. You know, okay, so e would cancel out the natural log and get us back here. But maybe a little bit more detail would be helpful. Maybe you're asking that, maybe not. If you are, here's what we did. We wanted to know the answer, limit as x approaches 0 for y. So what we did was say, okay, I'm going to do the limit as x approaches 0, e raised to the natural log of y. Well, that would be the same thing. That's still y. But because of continuity, because an exponential is continuous, I can do e raised to the limit x approaches 0 for the natural log of y. So this is what we did. And that allowed us to use L'Hopital's rule. We just made sure to put our final answer back into the power of e. So that whole thing came to 0. So then e to the 0 gave us our answer of 1. And maybe a little bit more explanation there is helpful for you. Maybe not. Maybe it made sense. Okay, anyway, whatever the case, that's it. That is L'Hopital's rule 4.4.